In the previous lesson, we completed our study of electrostatics in free space. We defined the electric dipole, derived the energy stored in charge assemblies, and introduced the energy density, WE equals 1/2 epsilon 0 E². Today we move to Chapter 5, Electric Fields in Material Space. We will classify materials by their conductivity, define convection and conduction current densities, derive the point form of Ohm's law, and examine how conductors behave in static electric fields. So far, we have studied electric fields in free space, a vacuum with no material present. But real engineering involves conductors, insulators, and semiconductors. How do we classify them? The key property is conductivity, sigma, measured in Siemens per meter. A material with high conductivity, sigma much greater than 1, is a metal or conductor. Copper has sigma around 5.8 times 10 to the 7th. A material with low conductivity, sigma much less than 1, is an insulator, also called a dielectric. Glass has sigma around 10 to the minus 12. Materials in between, like silicon and germanium, are semiconductors. At the atomic level, the difference lies in the number of free electrons available for conduction. Metals have an abundance of free electrons in the outermost shells. Insulators have very few. Semiconductors can be engineered to have a controlled number through doping. Before studying how materials respond to electric fields, we need to define electric current precisely. Current I is the rate at which charge passes through a surface. I equals dq over dt in amperes. The current density J is a vector, the current per unit area. The total current through a surface S is I equals the integral of J dot ds. There are two types of current density we consider now. First, convection current. This occurs when charge moves through free space. No conductor is needed. If charge density ρV moves with velocity u, then J equals ρV times u. A beam of electrons in a vacuum tube is a convection current. This does not obey Ohm's law. Second, conduction current. This occurs in conductors. When an electric field E is applied, the free electrons drift with an average velocity proportional to E. The force on an electron is F equals minus EE. Balancing drift against collisions gives J equals sigma E. This is the point form of Ohm's law. It relates the current density at a point to the electric field at that same point. Sigma equals ne²τ over m, where n is the electron density and tau is the mean time between collisions. The point form J equals sigma E is the microscopic version of Ohm's law. Let us connect it to the familiar circuit form V equals IR. Consider a conductor of length L, uniform cross-sectional area S, and conductivity sigma, with a potential difference V applied across its ends. The electric field inside is uniform, E equals V over L. The current density is J equals I over S. Substituting into J equals sigma E. I over S equals sigma times V over L. Rearranging, V over I equals L over sigma S. This gives us the resistance, R equals L over sigma S, or equivalently, R equals rho C times L over S, where rho C equals 1 over sigma is the resistivity. For a conductor with non-uniform cross-section, we use the more general formula, R equals the integral of E dot dl divided by the integral of sigma E dot ds. This is the field-based definition of resistance. Power dissipation follows from P equals the integral of E dot j dv. For a uniform conductor, this reduces to P equals Vi equals I² R, Joule's law. Now let us examine how a conductor behaves when placed in an electrostatic field. Consider an isolated conductor, not connected to any source. When an external field EE is applied, the free charges inside the conductor redistribute almost instantly. Positive charges shift in the direction of EE, negative charges shift opposite. This redistribution creates an internal field EI that opposes the applied field. Equilibrium is reached when EI exactly cancels EE, so the total field inside the conductor is zero. This leads to three fundamental properties of a conductor under static conditions. First, E equals zero inside the conductor. Second, since E equals negative nabla V equals zero, the potential is the same everywhere. The conductor is an equipotential body. Third, since nabla dot D equals rho V and D equals zero inside, there can be no net charge density inside. Rho V equals zero. Any excess charge must reside on the surface. These are not assumptions. They are direct consequences of the abundance of free charges and the static equilibrium condition. Let us work through example 5.3 from Sadiku. A wire of diameter 1 mm has conductivity 5 × 10 to the 7th Siemens per meter and 10 to the 29 free electrons per cubic meter. An electric field of 10 millivolts per meter is applied. Find the charge density, current, and electron drift velocity. The free charge density is ρ-V equals n-E, which is 10 to the 29 times minus 1.6 times 10 to the minus 19, giving minus 1.6 times 10 to the 10th coulombs per cubic meter. The current density is J equals sigma E equals 5 times 10 to the 7th times 10 to the minus 2, which is 500 kiloamperes per square meter. The current is I equals J times S. The cross-sectional area is pi d squared over 4 equals pi over 4 times 10 to the minus 6. So I equals approximately 0.393 amperes. The drift velocity is U equals J over ρ-V, which is 5 times 10 to the 5th divided by 1.6 times 10 to the 10th, giving 3.125 times 10 to the minus 5th meters per second. Notice how incredibly slow the drift velocity is, about 30 micrometers per second, even though the current is significant. Let us summarize today's key results. Materials are classified by conductivity sigma. Conductors have high sigma, insulators have low sigma, semiconductors are in between. Convection current density is J equals rho minus Vu. Conduction current density follows Ohm's law, J equals sigma E. Resistance is R equals L over sigma S. Inside a conductor under static conditions, E equals 0, the conductor is equipotential, and any excess charge sits on the surface. In the next lesson, we will study polarization in dielectrics and derive the modified form of Gauss's law for materials.